Hey, okay, so I think recording this might be a little bit faster. Okay, so so in this problem, we have a gun and it's firing a bullet, and the bullet's released from the gun. It ends up stuck in this block of wood, and then it's going to rise up some certain height in the air. Okay, so let's like talk about a systematic way to deal with what's going on. So this is conservation of energy and conservation of momentum. Um, Conservation of momentum is always going to be when you have some kind of a collision. You need to, I would look at the figure and model things as states. So notice that between state 0 and state 1, we have this collision. This bullet is going to collide with the block, and then they're going to move together. So between 0 and 1, we have conservation of momentum. And then between 1 and 2, we have something moving with a velocity, and it's kind of changing position, but we don't have a collision. So 1 to 2 is going to be conservation of energy. So cons of energy and then cons of momentum. Okay. So how do we set things up? Okay, so let's start with I kind of want to do momentum first, but I know that this is problem B, so we're going to look at problem B first and then number A. Okay, so for problem B, we have this bullet. It's going to collide with the block, and then they're going to move together with a shared velocity. So the way that we're going to do this is we're going to set up the initial momentum of the system is equal to the final momentum of the system. So initial momentum is equal to final. So we're looking at state 0 to state 1 because that's when our collision happens. So at state 0, we know momentum is equal to mass times velocity, okay, and it's a vector. But we're only moving in one direction, in the y direction, so we just can look at it as this is really like the momentum in the y is mvy. But it doesn't really matter. We can kind of leave it out because we're just dealing with one direction right now. Okay, so we have the mass of the bullet times the velocity of the bullet, okay, for the first, so each object with mass times its velocity, and then we have the mass of the wood times the velocity of the wood, which is going to become 0. And because it is an inelastic collision, they're going to stick together, so it's going to be the two masses times their shared velocity here, okay? So when we set up our equation and cancel out those pieces, this is what this looks like, okay? So we can get an expression for VB here, which is what I think they ask you to solve for. But I think it's more important to just sort of understand the general setup and why, okay? So we just set the momentum here equal to the momentum here. So to do that, all of the objects with mass times their velocities. And then if something sticks together at the end, we're going to add the mass together, and then they will have the same velocity at the end. So this is inelastic. Okay. Then for state 1 to state 2, so we have state 1 over here. Now they're stuck together and they're going to raise a certain height. So they're stuck together and they have some velocity. Okay, so we have some object with velocity and it's moving between state 1 and state 2. So we can use conservation of energy. Okay, so this is a general equation for conservation of energy. So generally you can use it in any case where we have energy in the system. A lot of these terms might cancel out to 0, but let's look at kind of the general approach. So we just have the initial kinetic and potential energy. So this could be like spring potential, gravitational potential. You can plug in any kind of potential energy that exists at this state. So at this state, we just have the velocity of this object, and we're going to model this as height is equal to 0. Then we're going to say height is equal to some final height here. Okay, so we're just going to choose this to be the initial height that we start from. Okay, so we're going to say that our potential energy or gravitational potential energy is 0. We're going to have the two objects stuck together and then 1/2 mv squared. Non-conservative work would be, say for example, this block is, there's some sort of friction force. I don't know why maybe it's like sliding up against something. And this frictional force would be opposing the direction of motion or something like that. When we have non-conservative work, it is the force in the system that's parallel to the direction of motion, okay, multiplied by how far it travels, okay? If, for example, I had, if it was going up that wall and then there was some sort of a force that was up at an angle, I would still need to find, and say this is like the distance that's traveled, or we'll say this is h here. We would still need to find the force that would be acting parallel, right? So in this case, it would be, we would need this this component. We need to find this piece, which would be like F cosine of that angle. So we just need to, if we have a non-conservative work, it just basically means there's some outside force, it's acting across a distance, and we need to put it into the system. So whether it's positive, so it's going to be positive if it's putting work in, so work in, and it's going to be negative if it's work out. So in the case of friction, it would be negative because it's work out. But in this case, we don't have any of that. But just as a general way to set it up, that's what's going on. Okay. For potential energy at the end, it's going to be raised a certain height, and then it's going to come, there's going to be no final kinetic energy. It's going to just hit its maximum height. Okay, so then we just plug everything into our general expression. We get this side is equal to this side because we have a lot of zeros, and we can solve for that velocity of the wood, right? Which is the velocity of this object here when they're stuck together right at the beginning. So this is that initial velocity of the wood, and then it goes up a certain height. Okay, cool. All right, so then the third part, for part C, they ask us for impulse. Impulse is just, it just means change in momentum. The way that they phrase this is a little bit confusing, but they say, what's the magnitude of the impulse of the block of wood during the time, so starting before it is struck by the bullet, and then until it travels upward to its highest point. So it's basically saying we want to find it, so starting before it struck the bullet, so that's, we're going to call this like T1, so starting before it struck, and then at the end where it comes up here. So to find the change in momentum, we'd have to find the momentum of the wood, because they ask just specifically about the wood. So this is, you know, mass of the wood. This is, again, the piece of wood here. Maybe I'll just box them. Okay, so here, okay, so what is the momentum of the wood here? So the velocity of the wood here is 0 because it hasn't been hit by that bullet yet. Nothing's happening. Velocity is 0 at T1. And then up here at the top, the velocity of the wood at the top is also 0, right? Because it's going to lose all of that kinetic energy as it's converted to potential energy. So it's actually not no velocity at the top there either. So if I try to find the momentum is mass times velocity. If I plug in the velocity at those 2 points, so this is just momentum at time T1 and at time T3. So they're just 0. And so, yeah, the whole thing is just 0. Okay, so the change in momentum is 0. No momentum gained or lost. Nothing really going on there. If it did have a velocity at one of these points, it would be very different, but this is still the same approach you would use. Okay. Then the last piece, it says, or the second to last piece, so for D, it says, what is the ratio of kinetic energy of the bullet before the collision divided by the kinetic energy of the collision, the block immediately after? So before the collision, if we take a look here, before the collision would be state 0, and then immediately after would be state 1, right? Pre-collision, post-collision, immediately after. Okay, so now let's look at that. So at state 0, for the kinetic energy, we just had, I can look over here. We just have at state 0, they're two separate objects, so we look at both of the masses, right? Okay, and then whatever velocity they might be traveling at. So the only thing that has velocity at state 0 is this guy here, and then the final, after the collision, then these two masses together have this velocity here. So it wants the ratio of the initial kinetic energy divided by the final, okay? So this would be just our initial, just this little bullet moving, and then the final is the bullet stuck in this block moving, so it doubled the velocity here. Okay, so we just divide those, and you should have these constants kind of at this point. Okay, then the last piece, it says, instead of getting lodged in the block, the bullet broke through the block of wood so that the bullet was traveling at 1/4 of its initial velocity after passing through the wood. What is the velocity of the block of wood immediately after the bullet passes through? Assume that the block remains intact other than the small hole created. So it's going to pass through, okay, and then they kind of both be moving. So, okay, again, we're going to look at this as state 1 and state 2. So this is like pre-collision, and this is post-collision, right, before it hits the block. So immediately before, immediately after. So immediately before, again, we have the velocity of the bullet, but the block isn't moving. So velocity of the bullet, so this is the momentum. So the sum of all of the momentums before. Maybe I should write this. Maybe that's a little more clear. So adding them all together, sum of all of them. So I have this one, but then the velocity of the wood is 0, so no momentum there. And then at the end, because they're two separate objects, in this case I have an elastic collision where they are going to separate. Inelastic is where they're stuck together. So up here, remember, we had inelastic and they were stuck together with one shared velocity. Down here, we have elastic where they're separate and they each have separate velocities. And we know one thing, we know that this velocity here is going to be 1/4 of the initial velocity here, because that's what they told us in the problem statement. So that kind of helps us with our algebra. Okay, and then we have the mass of the wood times the velocity of the wood. So actually, I think they use the subscript 2, would like 2, just because it's kind of like a different condition. And so then all you need to do here is just solve for this piece. So, okay, so then just to recap what we did. So we looked at we called these states, we called these separate states, and anytime we had a collision, for a collision, we modeled momentum before and momentum after. And then anytime we had just some object moving with some velocity, kind of over a distance, we looked at this sort of as conservation of energy. We noticed that we didn't have any non-conservative force, so we didn't have any outside forces acting on the distance traveled, and not even any forces that were like kind of at an angle where we would have to look at what component of the force would be acting in the distance traveled. So we didn't have any of that happening in this problem, and kind of explained why. So we remember that we can use this as a general conservation of energy equation. Anything can go in here. We just plug in all of our terms and we can set up and solve for things. So a good systematic approach. We looked at what impulse meant, just the change in momentum between two different states. They asked us for specific states, so we found those states. And then we found initial and final kinetic energy. And we showed the ratio, and we showed that for this inelastic collision, that this kinetic energy is not necessarily the same. But I do want to note that for elastic collisions, or where they bounce off each other, in that case, then the kinetic energy is conserved. But in this case, notice that it's not. It's going to be different. This ratio is different for inelastic, or where they stick. Okay. And then at the end, we solved for a different version where we did conservation of momentum between this state 0 and state 1 before the bullet hit the block, and then after it hit it, and then they separated. So we have an elastic collision where they have their separate velocities at the end instead of the shared velocity, and then the problem just asked us to solve for that piece. So I'll send the notes to you. Sorry if this is a little bit long. Hopefully this is helpful. Let me know if you still have any questions.